Welcome to video lecture B1. This one is on vector spaces. I'll be your instructor, Tom Roby. And here are the outline and objectives. We want to use our powers of abstraction now. We've looked at a lot of very concrete examples of linear algebra, but we want to see the full power of it, even the full power within matrices with real entries. To understand that, we need to abstract what is the essential qualities of things like a vector and linear transformations in general. So we're going to isolate the essential algebraic axioms we need for linear algebra, generalizing our notion of vector to capture a much wider range of examples than we've originally seen just with like column vectors with real entries. And then we'll analyze whether certain sets satisfy the axioms necessary to be considered vector spaces. So the first question I would ask you is, what makes something a vector? Right? If you've taken a physics class, you might have heard that a vector is something that has magnitude and direction, which is just a way of distinguishing it from, a scalar, which just has magnitude. But for us, mathematically, we actually want something that's much more general than that, much more abstract, but still, and we focus more on the operations in question rather than, what does magnitude and direction mean if we're talking about spaces of functions or something like that. So we're going to say that one of the things we want to be able to do with vectors is we want to be able to add two of them. So if you've got two vectors, v and w, you should be able to add them and get another vector, v plus w. And we also want to be able to rescale a vector, right? If I've got a vector and then I've got some scalar, so usually we're thinking of our scalars as being the real numbers, but it's perfectly plausible to have your scalars be the whole set of complex numbers. That comes up quite a bit. You can even have finite fields used as your sets of scalars. It's really a very general concept, even though in this course we focus on real vector spaces. And so here's an example that you might not have ever thought of as being a vector. Polynomials, right? So how is a polynomial a vector? Well, a polynomial can be a vector because I can add two of them, right? So suppose that p of t is, 1 plus 2t plus 3t squared. And suppose I want to add that to q of t, and maybe I'll write little vector bars on them so that you know that I'm thinking of them as vectors. Suppose this is, I don't know, negative 2, and then minus t squared, right? Well, it's clear that I can add these, right? No problem. P plus q at t is just going to be negative 1 plus 2t minus 2t squared. Okay? Or if I wanted to take p and if I wanted to know what 2 times p was, well, that would just be 2 plus 4t plus 6t squared, right? So it's clear that I can add two of these things, or I can rescale them. Okay, so that's what I need for something to be a vector. Doubly infinite sequences. So if I have sequences that just go, I don't know, the simplest sequence might be the integers, right? Dot, 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 minus 2, minus 1, 0, 1, 2, dot, dot, dot. Now I've got some other doubly infinite sequence. Maybe I have, negative 4, negative 2, negative 1, 0, 0, 3, dot, 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 right? And I just add those things term by term. So I guess I'm going to call that a 0. And so then I get negative 6, negative 3, negative 1, 1, 2, 3, right? And it's also clear that if I want to rescale it, I can just multiply each value through by 2 or a half or whatever I want to rescale it by. Okay? So doubly infinite sequences are another good example. If I look at the set of all of them, they'll end up being what we call a vector space. I can look at functions, real valued functions on the whole real line or on the interval a, b. And so what do I mean by that? So I could just say, right, if I've got some function f, let's use this pen. Suppose I've got a function f that goes from r to r, and maybe it's got a formula, in which case I can add the formulas, and g also goes from r to r. But I could think about their graphs maybe. So if they were continuous functions, then I'd have, some function that looked like, maybe a function that looked like e to the x. And if I want to add it to a function that does, something like this, well, then I just add it at each point, right? So this plus this is, I don't know. I didn't think about this ahead of time. But it looks like it might do something like this, right? Maybe if I add those two point by point. So I can add those, and certainly if I know what a function is, I know what twice that function is. So that's another good example of something where I can do addition and rescaling. And a fourth example is matrices, right? Certainly I know how to add two matrices, right? So if I have something like 1, 2, 3, 4, 5, 6, I can add it to 2, 1, 3, 7, 2, negative 1, right? And I know how to do that term by term. Or if I want to take one of these matrices and multiply it by 2, I just multiply all of the entries. So in all of these things, it's easy to see that everything I want makes sense. And so now let's look at what are the properties that I want to have. Okay? So the first property is that if I have, for the first, there's actually 10 properties. So there's 5 more coming here. These are all the ones that just deal with addition. And then there are a bunch that have to do with scalar multiplication. So all of these properties are natural. They're not going to cause you any trouble. The fact that there's a lot of them shouldn't be such a cause for concern. So, but here's an important one. If u and v are vectors, then u plus v has to be a vector. It can't be something else, right? If I tried to look at the set of all polynomials with only odd coefficients, then when I added 2 of those, I might get some with even coefficients. So that wouldn't count as a vector space. So I always have, this is called the closure property, and it's pretty important. This is the associative property. It shows up all the time, and it's never causes you any trouble in this class, right? What it says is that if I want to add 3 things that make sense, I can either add the vectors u and v together and then add w to it, or I can add u to the sum of v plus w. It's not a commutative property because I'm not changing the order. It's always u, v, w in that order. This one says that it doesn't actually matter what order I do it in. U plus v is equal to v plus u. That's a property that's not true if we were doing matrix multiplication. A times b is not b times a. This property was true for matrix multiplication, though, the associative property, because that's just saying if I compose 3 linear transformations in a row, then I can think of it in, we went over that earlier. You can think of it as either combining the first 2 and then the third, or combining the first with the combination of the second and third. Okay, there has to be a 0 vector. It has to be some vector that you add to, and that doesn't change anything, right? So what would the 0 vector be up here? Well, then we have a 0 polynomial, right? So add the 0 polynomial, 0 plus 0t plus 0t squared, and so on. Here, if I have double infinite sequences, what do you think the 0 vector would be? Right, just all the zeros. For functions, what's the 0 function? Makes sense, right? It's just the thing that's all zeros. And if you added that function to another function, you wouldn't change it. And for, say, 2 by 3 matrices here, just the matrix of all zeros, right? So they all have a 0. And they also have an additive inverse, right? If I want to find some matrix that I add to this matrix so that I get 0, I can just take -1, -2, -3, -4, -5, -6. And if I add, I'll get 0, 0, 0, 0, 0, 0. Okay? I think I'm going to give up on that red pen. It's really not visible. So -1, -2, even though red is the right color for negating something, right? And I just end up with all zeros. Okay, good. All right, so those were the axioms for addition. And now here come the next 5. These all involve scalar multiplication. Sometimes there's some addition as well. And so what this says is that, so the 6th one is again, so 1 and 6 are both closure axioms. This says that if I take a vector and I rescale it, then I always get another vector. So this means that I won't have a vector space if I say, look at all vectors whose length is no longer than 2, right? Because I could multiply it by, could take a vector of length 1 and multiply it by 3, and I'd get a vector of length 3. So I can't do some restriction like that. I always have to allow myself to rescale things arbitrarily. Now this says that if I rescale the sum of two vectors, well, I could have rescaled each of them and then added, right? So think about that here, right? Suppose I took 2 times this matrix plus 2 times this matrix. What would I get? Well, I get 2, 4, 6, 8, 10, 12 here, and here I'd get 4, 2, 6, 14, 4, negative 2. And if I add those things, you'll see that you get exactly the same thing as if you had just added them and then multiplied the 2 outside. So that's what this one says. It's a kind of distributive property. It says that scalar multiplication distributes over vector addition. Now, this one's a little bit different. This says if I have 2 times a vector plus 3 times 2 times a vector plus 3 times the vector is the same as 2 plus 3, 5 times the vectors, right? And that should make some sense to you if you take, you can pick any one of these examples that you want to think about. But if you take, so 2 times p of t made sense here, right? And if I took, oh gosh, I'm not sure what to write here, but if I took 2 of these, I'd get this. If I took 3 of these, I get 3 plus 6t plus 9t squared, right? And so if I add both of these things, then I'll get 5 plus 10t plus 15t squared, which is exactly 5 times that. Okay. Here, if I rescale a vector by d and then rescale that by c, that's the same thing if I just rescaled it by cd. Right? So now you're thinking about taking 2 times this, then multiplying that by 3, then you get 6 plus 12t plus 18t squared, which is the same thing as if you multiplied this by 6 to begin with. Okay? And finally, it has to be true that there's this one element in the real numbers, and when you multiply 1 times u, you just get back what you started. Okay, so that shows you that rescaling by 1 does what you think it should do, because otherwise you could define a vector space that would have some screwy thing where multiplying by 1 rescaled you more than you thought, and so then everything would be rescaled off by some factor. Okay, so these are the 10 properties of a vector space. Again, we'll see 1 and 6 again. This closure axiom is really important because these are the 2 things that might not be satisfied if I define some sort of arbitrary space of functions. And the other thing that's really important is there has to be something in there. So you might as well check to see that 0 is there since there has to be 0. And so that's coming up in another video lecture. Now there are other properties of vector spaces that look about the same as these, right? So one property is if you multiply 0 times any vector, you get 0. Okay. Why isn't it on the list? Well, because mathematicians like to make minimal lists. We like to just assume the minimal amount we need and then prove everything else from that, and we find that cleaner. So, like Euclid had 5 postulates and some common notions and things like that. Here, we don't need to prove that. We don't need to assume this as an axiom because we can actually prove it pretty easily from this. It actually follows from, u times, if I put 0 in for both of these, then I get 0 plus 0 times u equals 0 times u plus 0 times u. So 0 times u equals twice 0 times u, and the only way that can happen is if 0 times u is 0. We saw an argument like this earlier when we were talking about linearity. C times 0 is 0. Same kind of thing. Probably you're going to use this version of the distributive property. And when I multiply a vector by -1, that's the same thing as creating its negative, the thing here that when you multiply, when you add it to. I guess I didn't talk enough about this one. I did talk about this, right? So this is like the negative of some vector always exists in the vector space. So I couldn't, for example, look at only matrices that only had positive entries, because then I wouldn't be able to create a matrix like this that had negative entries to get the 0 vector. Okay, so I couldn't just assume that I couldn't look at the set of all matrices with non-negative entries. Okay, so let's see, are there any other examples I want to do? Let me just do one more with functions, right? So if I look at 3 plus 2 times the sum of two functions, x plus e to the x, assuming that I've got formulas for my functions, then the question is, what should this be equal to? This should be equal to 3 times x plus e to the x plus 2 times x plus e to the x. Okay? But that's clear, right? Because this is 5 times x plus e to the x, and this is going to be 5 times x plus 5 times e to the x. So none of these is hard. They shouldn't give you any trouble. And I've pointed out the ones that we'll be focusing on in the upcoming lectures. So I think that's all for video lecture B1. Thank you for your kind attention.